sorry for the delay. Yeah, I may need a new tablet soon because this one is probably like 5-6 years old. Okay, so today we're going to start chapter 24, which is actually the last chapter we're going to cover before we do our midterm. So we're going to finish up chapter 24 this week, and then next Thursday. Anyone know what next Thursday is? Yeah. What day is it?
The 23rd.
The 23rd? Let me just double check. Okay. I think all the electronics today are against me. So probably because I'm doing things last minute. The 23rd? Yeah. Let me just check. Next Thursday. Okay. Yeah, so midterm 1, right, which covers chapter 22, 23, as we state today, 24 also, right? It's going to be on Thursday next week, February 23rd. Those of you who had me before kind of already know what to expect on the midterm. It's kind of like what we did do in the group work, right? But then there's 3 problems and you have to do it by yourself. And so you just need a piece of paper. Well, you don't even need paper. You need a pencil, eraser, and a calculator. So make sure you have a calculator that you know how to use, because there will be some number you have to crunch. Yeah, so question?
Only 3 questions?
Yeah, so the first midterm is only 3. The subsequent ones will be 4, because we're just kind of giving you the first midterm to shorten the first midterm so you have more time to just kind of practice taking tests, okay? Yeah, so the first midterm is only the first 3 chapters, and then the next one is going to be 4 chapters, and then the third midterm will also be 4 chapters, and the final will be, like, I think 3 chapters plus cumulative stuff, okay? And last semester, we usually have a little review session for it the Monday before, so that's going to be next Monday, right? So we're going to be doing a little review thing where you guys, I'll put a little assignment on Canvas. You guys can post the questions you want to talk about, and then we're going to go through those on Monday, okay? And so that's going to shift our schedule a little bit, right? Because it's going to kind of devoting half a week for this. So that'll be 22nd. That'll be the 20th, right? So I have a little Canvas assignment for that, okay? Okay. So when we cover chapter 25, it's going to be a little bit wonky for a little bit, but so we'll have this half chapter situation for a while, okay? But when midterm 2 rolls around, it'll shift again and it'll fix everything, okay? So so today we're going to cover Gauss's law. This is actually a very neat picture. I don't know if it's still in your textbook. This was in the 4th edition, which I have in my office. So what's happening here is that this is someone's blood, right? There's all these color in the blood, and that's because, you know, different components of a blood actually are different color. It's mostly red because when red blood cells are exposed to oxygen, they do, the iron actually makes it a red color. But what they did is they just put a needle here, that's a conductor, right? And this needle has like has a bunch of positive charge, which is something we learned about, right? So a bunch of positive charge. It's not good color. It's a good color on top of this. Let's just keep doing green. Okay, right? And this creates an electric field going outward, right? As we learned last time, when you have a very long rod, right? And you're just measuring the electric field around that rod, it just kind of points outward away from that rod, okay? And what happens is that this electric field causes the molecules, certain molecules to move outward more and other molecules to move outward less, okay? And I don't know the biology of it, but then you can separate different parts of your blood just by applying an electric field to it, which is sort of neat. And the reason they do this, I think there are certain cells that are blood cells that are not, let's say it is not behaving correctly. So I think this picture is a healthy cell, but you can detect cancer with this because like certain cells will not go outward in a certain amount because they are, malignant or growing out of control or something like that. So you can actually separate different parts of your different cells in your blood by applying electric field to it. And the thing we want to also get from for this chapter is that you notice this, this rod situation is kind of nice, right? Because it gives you the circular pattern, right? And we're going to talk about this thing called symmetry, right? This is a circular symmetry, so everything's just kind of going in a circle. And this is going to take us into this idea known as Gauss's law, which is the main thing about this chapter. But before we can talk about Gauss's law, we have to cover two things. The thing I talked about, symmetry, and also this idea of flux, which is going to be the first two sections of this chapter. Okay, just give you guys a little history. As usual, the Gauss's law is named after someone named Gauss, happened to be Carl, just a sort of always a neat name, Carl. There's a circle up here. Okay, right, and he lived in the early to mid 1800s. So so there's no photographs of him. So this is a little painting of him just standing around, I guess, his telescope and his chair. I don't know. I guess his two favorite thing in the world. But he's one of the mathematician plus physicists who kind of develop electricity and magnetism in the way we understand it today. And he is actually kind of cool because you notice how complicated it was for us to calculate electric field last chapter, right? He made it easier. Okay, so this guy is actually being nice to us. Once we understand this concept called Gauss's law, it actually makes calculating electric field for certain geometry actually much easier. Okay, which is always a nice thing for me because you know how I struggle with a lot of calculations, right? So making the math easier for me is actually, I always like these guys who can make the math easier for me to do. Okay, but the concept we need to know about this, the first thing we need to know is this idea of symmetry, right? As we already saw in the little blood pattern, right? When you apply an electric field to a rod, an electric field from the source is a rod, right? There's this circular symmetry around it, right? So if you have a long rod, right, all the electric field kind of points away from it, right? So I'm going to stop using my hand and use my tablet. The electric field points away from it, right? I'm trying to do like a little perspective drawing here also, right? That's coming out, right? It's kind of like, imagine like a little fan, right? That's kind of coming out like this, okay? This gives us circular symmetry, right? Because at every point on some radius outward, like this, the electric field strength is actually the same, no matter how far where you are on that circle, that purple circle. Okay, and that's an important point that we're going to use today. Okay, in order to simplify our calculation. Okay, just a little side note: symmetry is also very important in like all of physics and all of science, also not just physics. So whenever you guys are doing your research or doing some sort of lab work, right, knowing the symmetry of the problem is actually very useful. In that way, you can do calculations or make predictions that otherwise you will not. One of the most famous symmetry is the matter-antimatter symmetry. So we ourselves, just because we are made, we are the one who gets to call things, right, name things. We call ourselves, the stuff we're made of, matter. Is, all the protons, all the neutrons, all the electrons around us, okay? There are these things called antimatter, right, which is exactly like us, but has the opposite electric charge, okay? So in the antimatter world, there's something called an antiproton. So instead of having a plus charge, this proton has a minus charge, okay? And in antimatter universe, right, or in the antimatter land, right, instead of an electron having a negative charge, it has a positive charge. Everything in that particular part of the universe will work exactly the same way. You can make lithium atoms, for example. So lithium atom has 3 protons and 4 neutrons, okay? And have same number of electrons just to neutralize the charge, okay? In the antimatter land place, right, you can make anti-lithium out of antiprotons and anti-electrons called positrons. So this is just a and so as opposed to call it anti-electrons, they just call it positron. And the entire that place can actually work exactly the same way we do. Okay, right? The only difference is that they have opposite charge. Okay, but the problem happens if the antimatter interacts with regular matter. If you guys, anyone knows what happens when antimatter interacts with regular matter? Anyone's? I'm sorry?
Does it just blip out of existence?
Well, it changes all of that matter energy into, all that matter into pure energy instead. So if you ever have a regular proton interact with the antiproton, okay, and in particle physics they call it P bar, right? If they ever interact with each other, all of that mass energy will just get released into S energy. And this is where the Einstein came up with this E equals mc squared equation, where whatever mass of this proton is, actually twice the mass of the proton, right, gets converted into pure energy, and that's because of this balance between matter and antimatter. And it's sort of a neat thing that, you know, we call ourselves matter, but there could be part of the universe out there that are completely made of antimatter, and we just don't interact with it. That's why we don't notice it, you know. And then if you go there and you land your spaceship and you end up actually blowing up the whole planet, because you're basically having a bunch of matter interact with their antimatter, and then everything just blows up. Okay. So just be careful if you decide to go to like a galaxy far, far away. Just make sure they're made of matter first. Okay. And we call it matter, and we call them antimatter. It's just because our perspective, right? From their perspective, they are the matter, we are the antimatter, right? Okay. So this is sort of a neat thing about the universe that happens, and it's due to the symmetry between matter and antimatter. Just by flipping the sign, right, the plus charge to negative charge, right, that changes nothing about how they behave, how we behave, but when they interact together, that's when we have a different situation. All right, so enough of that little side note. That took like actually much more than I thought it would. But remember in chapter 23, the last chapter we had, right, we actually did use symmetry in that problem, right? When we calculated the electric field from a ring, right, at some point P along the z-axis, what happened was that we found that, you know, the electric field, each of the little pieces, right, was proportional to R, right? And the nice thing about this problem is that no matter where you are on the ring, the distance R here, and the distance R here, distance R here, they're always the same, right? So this is actually a circular symmetry problem because, right, by having the same radius, no matter where you are on the ring, make the integral that eventually we have to do much easier, right? Actually, we didn't even need to do the integral because we find out that, well, if you're able to pull this R square out, what happened is that you just have to sum up all the charge. And of course, the sum of all the charges on the ring is just the total charge on the ring, okay? And that's why we can do this step. So this is, by being able to pull this R out, right, that's due to the symmetry of the problem. Okay, this is the symmetry thing. Symmetry. Okay, so that's a rotational, that's what we call a rotational symmetry. It's because if you rotate this ring, right, no matter how far you rotate it, it will look the same to you, right? If you just imagine holding a ring in front of you and you just, you know, rotating the ring, right, it'll still look like the ring. You can't tell the difference unless there's some defect on the ring, right? Okay, it'll look exactly the same to you, okay? So that's the rotational symmetry. There's also translational symmetry. We actually kind of saw this also, where if we had a rod, just a stick that's pretty long, right? They call it in math line, we're just going to call it infinitely long because we don't actually care that much about, you know, how long exactly it is. Okay, if I was on this stick, right? No matter, let's say I'm living on here, right? Looking in this direction, there's just an infinite sea of charge going in both directions, right? But if I was to walk forward a little bit, right, I will still just see an infinite charge in front of me, infinite charge behind me. So that's known as translational symmetry. Okay. Translational symmetry. Okay. Because I can walk forward or backward, the place still looks the same to me. Okay. Okay. If anyone ever had go on a long hike, right, and then after like a few hours, the forwards just kind of look the same, right? It's not, but it feels like a translational symmetry situation there. Okay, especially with this rod situation, right? You can also think about a rod. If you just rotate it, well, it'll look exactly the same to you. The only way I can tell the difference that when I rotate this pen around is because they have these knobs right at the end. Imagine those knobs are not there. I just keep rotating it. It'll look exactly the same to you, right? The other thing, so this is rotational symmetry. Rotational, right? Right. Also, there's also flip symmetry or reflective symmetry, where if you take an object and then you just, look at it from a mirror, it will look exactly the same to you, and that's actually a reflective symmetry. We're not going to see too many of those, but it's just to complete the set of all the different symmetries that you could have. Okay. Going down to a more relevant example, okay, where let's say you have a rod, okay, and this electric field is not correct, but let's say the electric field looks like this, right, where it's pointing in this direction, at like 45 degrees, okay. If I flip this, right, around this dotted line, what will happen is that now the electric field looks this way, right? It's supposed to pointing slightly to the right. It points slightly to the left. That means you broke the symmetry. You can actually tell the difference, right? Right. Even though the rod looks the same, right? By flipping it 180 degrees, right? You can tell the difference. Therefore, this invalidates the symmetry, right? This cannot happen due to symmetry. Cannot happen due to symmetry. Okay, right? So just by symmetry argument, we know that these electric field lines cannot be correct. Does that make sense? Right? Because the rod has this reflective symmetry on it, right? But if you draw an electric field that does not behave that way, right, that breaks the symmetry, and therefore is actually invalid. And therefore, you know that these are wrong somehow, okay? You don't know what the right answer is, but you know that it cannot be correct, right? Does that make sense? Right? And therefore, just by symmetry argument, you can tell that, well, if you have a rod that is infinitely long, right, that the electric field has to always just point upward and not to the left or right at all, right? It just has to point away from the positive charges, the rod itself. Okay. There are more pictures of this. And we're going to utilize these three different symmetries. One is this plane symmetry, right? Plane symmetry is just kind of like a two-dimensional version of the translational symmetry we talked about. And it's supposed to just go in the rod in one direction, right? If you go in two different directions, everything still looks the same, right? Just imagine you're on a flat surface, and there's just infinite charge going out that way, infinite charge going that way in all four directions. No matter where you walk, you're just going to see infinite charge in every direction, right? So I mean, this picture is kind of misleading because it's drawing this edge here, but imagine this edge doesn't really exist. It's just these charges just keeps going, right? And the reason they have to put the limit on that drawing is because we have a finite size of a book, right? Right. So this is planar symmetry. Okay. The thing we all kind of already talk about is the other one's called the cylindrical symmetry, where, right, if you have a cylinder, right, no matter where you rotate it, it'll still look the same. Okay. This is cylindrical symmetry in this case. Okay. And then spherical symmetry, we're actually going to try that hopefully on Wednesday. I'll show you guys an example of cylindrical symmetry. You can imagine one of the most symmetric things is probably a cylinder, right? If you have a perfectly spherical object, right, no matter how you rotate that object, it'll look the same to you. Okay. And these are the problems that's going to apply to, where we're going to apply planar symmetry to, this is the reason why, right? If you have two parallel plates like this, like we had last time, right? Right. This is known as a capacitor, right? We kind of learned that nomenclature. Okay. We're going to apply planar symmetry. That makes sense, right? You have one plane that is, flat. The other plane is flat, right? There's going to be some electric field between it, right? We actually calculated that last time, right? If you're very, very close to the surface, right, it looks like an infinite sea of positive charge on this surface. If you're very, very close to this surface, it looks like an infinite sea of negative charge. So therefore, you can apply planar symmetry to that. Okay. The cylindrical symmetry applies when you have coaxial cables like this, where you have a conductor that's on the outside and then a conductor that's inside that's actually carrying your signal. Okay. Do these people ever see coaxial cables anymore? Like cable modems? Yeah, you still see those. This is the reason why they designed them. It's actually a way to cancel out noise also. Okay. If you have a sphere or more complicated things where like you have a sphere inside a sphere, right? You can calculate electric field between two different concentric spheres, and that's utilizing the spherical symmetry. Okay. Right. So these are special shapes. Okay. And we're going to focus on solving problem with these special shapes. Okay. And these special shapes has the symmetries that we can apply to it. And therefore, if an electric field, if we calculate some electric field, let's say it's pointing this way, we know this cannot be correct, right? Because it does not obey the planar symmetry, right? Because if I move over here, right, if I have the reflection here, right, the reflection of that will point the wrong way, right? And that's the idea where if you have this, the charge has to obey the symmetry, the electric field line that they produce also obeys the same symmetry. Okay? Okay. So these charges, right, is translationally the same, and then if you take the mirror image of this, it'll look the same. So the electric field also has to behave the same way. Okay? All right. Any questions before I jump to a completely different topic? Right, but we're going to sew these two together in the third section so that we can actually use this thing called Gauss's law. Okay. Okay. So this other thing we're going to need, which is actually going to be on the left-hand side of Gauss's law, okay, it's called flux. Okay, and this flux thing was completely baffling to me when I was learning this. But I think this textbook actually explained it very well with this opaque box situation. So let me just start off with this, okay? Let's say I have some positive charge, right? Right? Positive charge, right? It'll create electric field. Let me do that in a different color, right? That goes outward. Like that. Right? Away from it. Okay. There's some electric field that goes in every direction, going outward, right? Let's say I put this positive charge in some box that I cannot see through, so I cannot actually physically see the charge, right? But it doesn't interrupt. It doesn't disrupt the electric field. It doesn't absorb it, right? It's just the electric field can pass through it, right? So if this box is there, right, this becomes opaque, so I cannot actually see what's going on inside, right? But I can still see the electric field coming out of it, right? So from that, I can actually deduce that there has to be some net positive charge inside there, right? Right? Because if I open this box, right, I actually I do not know whether or not it's one single positive charge, or maybe 2 negative, 3 positive, right? But I do know inside that box has to be a net positive charge, right? For the electric field to be going outward from it. Does that make sense? Right? So we're going to do this these little thought experiment, right? Where if I have some opaque box, right, all the electric fields are going outward, we know that there has to be some net positive charge inside, right? The opposite example of this, if all the electric field is going inward, what type of charge should be inside? What do you guys think? Something negative has to be in there, right? So this has some negative charge in there. Okay? So this, the third one is the hardest one. What if the electric field just passes through it and there's no net electric field going in or out? So there's three, well, I wish they drew this closer. Right, there's three electric field going in, there's three electric field going out. What do you guys think the net charge is for the inside this box? 0, exactly. So you guys have been good on reading, because this, you know, probably would not be very intuitive, because, right, if there's no, well, if there is a charge in here, there has to be some field that comes out, even with just a tiny bit, right? Okay? Right? There has to be no charge in there, which is kind of neat, okay? So that's the box version, right? What we're going to do is we're going to apply these to the symmetry stuff that we talk about. For example, we can do one with cylindrical symmetry, where let's say you have a cylinder like this, right? So, and this is hard to see. So imagine all the electric field is pointing outward, but then, you know, it's pointing outward this way, this way, this way. Right? That, in that situation, right, it obeys cylindrical symmetry, right? But we know that inside here there has to be some positive charge that also obeys cylindrical symmetry, right? Because if the charge does not obey cylindrical symmetry, it will not produce electric field that is also cylindrically symmetric, right? Right? Even though, so this box, we're going to eventually call it a Gaussian surface. Just pretend this box is there to mask you from seeing actually what the charge is. Right? It's like the curtain of the magician, where, you know, the little thing it's not a curtain, the little handkerchief in the magician where they reveal what's inside. Right? Okay. Right? A lot of times it's hard for us to see these things in this perspective view. What you want to do is actually break this down into a side view and a top view. Okay, the side view is looking at the side of the cylinder without worrying about what's going on. Right? On the side view, right, for this drawing, right, we have just electric field going to the sides. Right? Right? We don't worry about the ones that's coming out straight at us. Okay? Just take a little slice of it and look at it. But the top view, right, if you're staring down at the cylinder, right, you're going to see electric field going all kind of like a brush going all outward, okay? And so this is a very useful way to dissect these complicated object into two simpler drawings, okay? Okay, so simplify a 3D drawing into two 2D drawings, okay? So that's a very useful thing to use, okay? So lastly, we also have the sphere situation. So if you have a sphere, right, and you have electric field going outward like this, okay, we know that whatever the charge distribution inside has to be spherically symmetric, right? Because, right, if we have a charge, you know, let's say a rod like this, right, that's not spherically symmetric, right? That means there's going to be more electric field going out here and more electric field going out here, but then there's less, should be less here, right? So this cannot be true, right? We know that whatever's inside here has to be a spherically symmetric charge distribution, just from looking at the outside, okay? Right? Imagine just, once again, this is just a little box that you put the charge into, okay? So this is not the real charge distribution. The stuff I drew in blue is the real charge distribution, okay? Okay. So this little opaque box thing, right, that's going to be confusing to well, myself when I first look at this, when I first learned this. And so don't get this mixed up, okay? This little orange surface that the book keeps drawing, it's just the handkerchief that the magician is using to hide what's inside that box, okay? Okay? And it's your job to actually figure out what's inside that box. What shape is it, right? What kind of symmetry it obeys? What is the net charge of it, and all that stuff. Okay. So these opaque surfaces, we're going to call them Gaussian surfaces because, right, it's named after that guy Carl Gauss, and we're going to apply this thing called the Gauss's law to solve very symmetric problems, okay, obeying the symmetry and flux situation, okay. So first of all, but the thing is, I talk about this idea of a surface with electric field going through it, okay. So whenever you have some sort of field going through a surface, I'm going to even try to match the color coding of the books. This is some surface, okay. And this can be either a real thing or an imaginary thing. Okay, it doesn't have to be real. Okay, right. In this case, if electric field is going through it, this is known as this combination of a surface plus the electric field. The surface. Let me rewrite that. Okay, electric field going through a surface. Okay, that's defined as electric flux. Okay. 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 All right. One simpler way to look at it is like if you have like a river, right, where some water flowing through it, right. You know, there's some, you know, let's say a pipe or something like that, right? The amount of water flowing through that little pipe, right? That's the flux of water going through that pipe, okay? So let's do this by just raise of hands, okay? Let's say, right, this little box right here, right? We don't know what the charge distribution is inside that box, okay? But we know there's going to be 1, 2 electric field line going outward, 1, 2, 3, 4 electric field line going inward. Okay, so what would be the net charge inside that box if those are the electric field lines going through those surfaces? So what is the net flux? Is it going to be inward or outward in the first place? It's inward, right? So the net flux is inward. Okay. Okay. And just by definition, we're going to call that negative flux, okay, if it's going inward. Okay. So what do you think the charge inside that box is? Is it going to be A, a positive charge? How many think is a positive charge? Is it B, a negative charge? A couple of you? Okay, maybe 6 or 7. Or C, there's no charge. Okay. 1. Okay. Or is there a net positive charge in the box? Okay, this is where reading the problem gives you the answer. Or is there a net negative charge? I mean, if you guys, those of you who answer B, right, if you want to change your mind, that's fine, right? Right, so this 8 and 9 of you guys, okay? Or there's no net charge. How many think there's no net charge at all? Right? Okay. So in this case, there is a net negative charge, and just to be careful, right, to differentiate it from just saying a negative charge. So we don't know what the charge distribution inside is, but there has to be the negative charge has to win over the positive charge in order for it to have a net flux inward, okay? Because otherwise, right, if there are more positive charge than there are negative in there, then there will be more flux going outward, more electric field going outward through that surface. Okay, so I'm going to show you guys how to calculate this electric flux thing. Okay, right. So as we saw, right, when you have some sort of made-up surface, or it could be a real surface, okay, real or imagined, right? When you have the electric field going through it, okay, what happens is that, right, if you take the electric field, right, electric field, if you multiply that by the area, I'm going to do the multiplication first without the vector stuff, okay? electric field times the area of that surface, right? That's going to be proportional to what we're going to call electric flux. Okay? And the electric flux is going to be symbolized with this capital phi. Just write a phi, but then put like 2 bars on the top and the bottom of it. Okay? Okay? Since this is an electric flux, we're going to put a little subscript E on it. Okay? Okay? So how do we figure out what this A is? The A in this case is pretty simple. It's the area of this box, right? The problem is that, right, the box, sorry, this little rectangle is not always going to align with our electric field, right? The box can be pointed this way. I'm just going to show you that, right? The box could be at an angle relative to the electric field, so we're going to have to deal with some vector stuff with it, okay? But seeing these 3 different examples here, right, where, well, if your little rectangle, right, let's say is at 90 degrees, right, there's basically almost no electric flux through it, right, because none of them kind of can pass through this way, right, if we have an electric field going to the right. Okay, so somehow having this little n vector here, right, if this n vector and the electric field vector, you know, is the angle between them is around 90 degrees, right, we basically get no electric flux, right? If this n vector and the electric field vectors, right, right, is basically aligned with each other, meaning their angle is about 0, right, then the electric flux is actually the maximum, right? Okay, so there's a function that tells you that, right? So you can choose between sine, cosine, or tangent, right? Which trig function gives you the maximum value when the angle between them is 0? And remember? Yeah. Cosine, right? Cosine of 0 is actually 1, right? But sine of 0 is 0, right? So you don't want sine, you want cosine. Okay? So therefore, if you just have some normal vector, so this is also known as the normal surface vector, right, where you have some electric field line going around it along the horizontal, okay, we can have a more generalized version of this equation where it's going to be the electric field times the area of that surface times cosine of the angle between them, okay, right? That's going to be our electric flux, okay, right? So that's what we get to here. 3 more minutes. Okay. So this angle theta, right, just as when we dealt with other dot products and cross products, when we did torque and stuff like that, right, it's very, very important for you to figure out what that angle is, right? Because a lot of times the problem will just give you some angle, but you don't know if it's actually correct angle, or is it 90 minus that angle, right? So this angle between the electric field, let's do this drawing here, right, and the surface, right, we're going to call this surface, right, we're going to make this surface kind of into a vector where this normal vector that I was drawing before, right, is actually pointing in the same direction, pointing in the same direction as this thing called an area vector or a surface vector, right? So if I have a surface like this, like my wallet, as opposed to, you know, pointing up and down, it's pointing straight out of it, okay? And as I rotate my wallet, right, the surface goes with it, okay? Okay? This is known as a normal vector, right? So we're going to define the surface this way, where A, the vector, okay, is whatever the area of this surface happens to be times the normal vector, which gives you the direction, right? So this gives you the magnitude, this gives you the direction, okay? Okay? So if we vectorize all this stuff, right, we can actually write this little equation, E times A cosine theta, as actually the dot product between 2 vectors, okay? The dot product between 2 vectors, okay? So if I have some A vector and some E vector, right, I want to take the dot product between them, okay? E dot A That's actually the magnitude of E, magnitude of A times cosine of the angle between them. So that's how I can actually define it this way. Okay, and this is really nice because, right, those of you so one thing you should always think about is that dot product tells you how parallel two things are to each other. Okay, if I have vector A and vector B and they're parallel to each other, that's where you maximize the dot product between the two. If they're 90 degrees to each other, the dot product is going to be 0. Right? If they're opposite of each other, the dot product is actually negative of that maximum value. Okay? The other version of this, remember, is that cross product. The cross product tells you how perpendicular two things are to each other, right? So that you want to always have that. I'm going to do the example tomorrow. That way I'm not taking you guys, making you guys late to the next class. So I didn't need to load those pictures anyway because I'll figure that out. Okay? All right, I'll see you guys tomorrow, and we'll do a little worksheet on flux tomorrow, okay? Stop recording.